Good evening, everyone. Can you all hear me? Okay, good. Okay, this is a continuation of the last part, which is chapter 9. I will not cover chapter 10 and 11. You can read through yourself the chapter 10 and 11. Okay, there's one part of this chapter 9 which is quite important because it will come out next. I'll tell you where. Okay, when I explain through it, I will explain also some example so that you know how to answer the question. Okay. Let me record first. Start recording. Okay, if anything wrong or you cannot see the screen, please turn on your mic and let me know. Okay, don't type on the chat box there because I wouldn't be looking at it. Okay, just turn on your mic and let me know. So, okay. Yeah, last week I discussed this part already, and I told you that you can solve this problem in parallel. And I see this morning also, some of you are doing processing that is kind of dependent on one another, especially like this kind of form where you have the first stage. Okay, they are independent across this what I call it task, but they are dependent uh, between the the stages. For example, this is the first stage. These four tasks are independent of one another. On the second stage, it relies on the previous task. You can see that Civic and 2001 actually relies on the data computed in this task and in this task. The same thing for white or green. But between these two, they are independent of one another. So that's why you can actually assign one thread to execute this, another thread to execute this. But this thread cannot start until these two previous thread has finished their computation. The same thing for this. So they don't have to wait for one another. For example, if these two finishes, this one can start before this. Although I show it to you like this, but it doesn't mean that this also have to wait for uh, this task to finish. Sorry, this task to start. Okay, so he has a choice to proceed without waiting. But of course, we want it to proceed because we do not want to wait. So you can see from here that you can actually break down your problem into multiple tasks. And I see this morning the student failed is because uh, maybe he did not do it correctly. He was doing it recursively. That's why he cannot get the correct answer. Okay, you can do recursive call in order to do this, but then it's very hard to get it right. Okay, that's the reason why I requested the team to actually modify the strategy so that they solve this problem using iterative method rather than recursive method. Okay, and the final part here, there's only one task that's running, but it's all right because here these are the hardest part to actually solve because it involves so many different piece of data here. Okay, as you go down to the next stage, please don't share your screen. Only me share the screen. Don't share your screen. Can you disable that? Okay, only me sharing the screen. Don't share your screen. Okay, so although here the last task actually run uh, alone, but because the previous task is running in parallel, and here we already achieve performance gain already. But definitely the last one, we don't achieve any performance gain. But it doesn't matter because the table is smaller. Okay, the, the previous task, especially at the top here, you have a lot of tables and a lot of search to get to your um, pointer. Any problem there? Is my screen is still on? It is, right? Okay, don't share your screen or don't override your screen on mine because I will not be able to know that you're overriding it. Check. Okay, I think I'm presenting this screen, right? Can you see, right? Okay, if you cannot see, please let me know. Okay, so this last week I already mentioned already that each task will look at the table, okay, and then solve only one particular part. Here, they don't really care whether they get to the solution or not. You can see that actually there's only one answer that you get here, but right over here, your table is actually quite huge. Any problem?
Also cannot see.
Can't see. Am I sharing? I thought I shared. Uh, your screen is still visible while someone else is presenting. I think somebody else is presenting. Can someone please not present? Uh, not sure what's happening here. Let me stop for a while first. Okay, don't share your screen because it will disrupt my screen, I believe.
Can already.
Oh, okay. All right. Okay, so I'll move on to the next one. Before I move on to the next one, this is one way to solve it. You can see that I solve it by looking at Civic and 2001, white and green. Okay, and then as I go down the hierarchy, I will converge these two to one. Okay, on the next uh, what do you call that slide, here is another way of solving the same problem. Okay, but this is slightly different in the sense that the first part actually is the same, but when it goes down the next level, you can see that there's only one that is task that is functioning. Okay, the other two is actually not processed. So this is actually not so good. Okay, although you can do this. Okay, because on this station you got only one task that is running, right? And what do? You converge these two so that you get white or green. And on the third stage, okay, the third stage you only take one of this, okay, and you merge with the previous result, and you get 2001 and white or green. Okay, and finally when you reach the last stage, you perform this. But this is not a good solution because you can see that the first stage actually is quite a lot of tasks, but in the second and the third stage, not much task that is running. Here, there's not much different. There are only four levels, the same as what you see here. Four level here. Sorry, here is three levels. So actually, this is much worse because there are more levels. Okay, why we do not want more levels? Because more level means they have to be waiting for one another. That means they're dependent on one another. Okay, so you can see these two is actually waiting until um, this stage is gotten and finally this stage. Okay, but finally you get the same answer as well. So it depends on how you decompose it. Okay, if you decompose them um, in balance, left and right, most probably you'll get better answer than non-balance like this. Okay. Okay, the granularity of the task, I think I discussed this before. It just tells you that how you can decompose your problem. For example, here I got task one, task two, task three, task four, right? So I don't do only one row, but I do three row at one go. Most probably because I don't have enough thread. For example, here maybe I got only four thread, but then I got so many rows here, so I need to share these rows among the same task again and again. Okay, so this is a decomposition by block. Okay, you block decomposition because each task is actually taking up several rows, several consecutive rows. Okay, so the granularity here is can be quite high. Sorry, in this case here is should be low because your task is more, your communication is less. Okay, so granularity maybe uh, what is talking here is about the size that you compute. Sorry, the complexity that you spend on solving the problem against the time that you used to spend to communicate with one another, exchanging information. Okay, so this is a coarse grain counterpart of it. So you have a high granularity here. Okay, coming back to the topic just now. So the degree of concurrency, as what we saw just now, um, it means how many tasks that you can break the problem into. Okay, so if you look at the previous problem, you can see that the maximum degree of concurrency is actually 4. For example, here, okay, if you look at this stage here, there are 1, 2, 3, 4. So the degree of concurrency on this stage is 4. On this stage is only 1. This stage is 1. This stage is 1. And the maximum degree of concurrency is taking into account all the stages. So the maximum is 4 because the top here is the largest one because we are looking at the maximum. Okay, looking at the first example, also the same. Different is maybe in the middle here. So the number of or the degree of concurrency for the first stage is 4. For the second stage is 2. For the last stage is 1. Okay. So here maximum degree of concurrency is also 4. Okay. And there's another term that we use is the average degree of concurrency. Just now we talked about maximum degree of concurrency. We look at the largest. The average perhaps is better choice because if we look at the maximum one, like for example in this case here, maximum here is 4, but it's kind of deceiving because the second stage and third stage and the fourth stage, each one of them is 1. Okay, so you might spend a lot of time here, a lot of time here, a lot of time here as well. But if you say the maximum degree of concurrency is 4, people would think, oh, actually your concurrency is very good. Actually, it's not because it only happened in the first stage. The rest of the stages, only one degree of concurrency, so it's not good. Okay, so perhaps we should use average degree of concurrency. That would be fairer because here is 4, the next is 1, 1, 1. So you add all of them up together. So you got 4 plus 1 plus 1 plus 1 is 7. Divide by how many uh, stages that you have here. So you divide by 4. 7 divided by 4. All right. So that is the average degree of concurrency. Okay. And here is 4 plus 2 plus 1. So 4 plus 2 plus is 7, but here is divided by 3. So the degree of concurrency, the average degree of concurrency is larger. So it shows to you that this actually is better than the other one. Okay. Okay. Another terminology that is quite important to know, which we use to measure how good our concurrency is the critical path. Just now we talked about the number of tasks that we can execute at the same time. That is the degree of concurrency. Now we want to look at the critical path length. Why this critical path length is important? Because the longer the critical path length, the worse the performance is going to be. Okay. Similarly, the degree of concurrency, the wider it is, that means the broader it is, the higher the degree of concurrency, the faster it is. Okay. That means you can run multiple tasks at the same time, so you can solve them in parallel faster. Okay. And the critical path here is related to uh, the path from the beginning until the end here, the longest path. For example, here, this is 1. Okay, from here to here is 1. Here to here is 2. You have to go through 1. Sorry. You have to go through one stage and have to go through the next stage here. Active stage here. This one is not active stage. So this is one active stage. This is 1 and then 2. Okay. Actually, I counted wrongly. It should be 2 here. 1, 2. Right. So that is critical path. Here should be 1, 2, 3. And here should be 1, 2, 3, 4. And here's 1, 2, 3, 4. Okay, so you got 2, 3, 4, 4. Right. So the maximum uh, uh, path is actually the critical path. So this is not the critical path. This is not the critical path as well. This one is the critical path because it involves 4 stages: one, two, three, four. Here also is a critical path. So the critical path determine um, your speed actually, because even though this finish faster, right? But it has to wait. The data has to wait until you process it here. The same thing for this civic. It has to wait at least 2 stages before it get computed, right? So the longest path actually determine the worst performance, okay? Because the rest of the way it cannot compute uh, immediately, right? It has to wait for white and green to complete first, and then finally when it reaches this stage, now it can be solved. So the critical path basically determine how slow your system is going to be. It can be used to determine uh, the performance or maybe predict your performance. Okay, so if you look at the previous um, example, the critical path is actually 3, 1, 2, 3. Here's 1, 2, 3. Here's 1, 2, 3. Here's 1, 2, 3. Okay, now I'm assuming that here we are assuming that the amount of time taken for computing computing this task is the same. Okay, let's say this one takes about 10 unit time, this one 10 unit time, 10 unit time, 10, then that is the uh, critical path. But sometimes it can be quite deceiving because uh, maybe this computation is a bit higher, is maybe 100 unit time, the rest is only 10. Although it looks like here is only like 1, 2, 3, right? You cannot count 1, 2, 3 right now because you have to take into account the complexity of the problem. For example, here I told you that it takes 100 unit of time, meaning that it's more complex to solve. Okay, so the critical path will be this. So we don't look at the number of stages, but we have to look at the unit time that it takes to solve the problem. By right, we should be looking at that rather than the number of stages. But here, we simply just use the number of stages here because we assume that every task is actually having the same amount of time to compute this or to solve this problem. Okay, so the critical path is actually the amount of work done to solve the problem. So that will be counted as a critical path. Okay, for example, in this case here, um, if let's say the critical path takes 10 times unit, that means 10, 10 units of time to solve the problem, and every one of them also the same thing, then we can just count the number of uh, node here. That will be your critical path. For example, in this case here, 1, 2, 3. Here's 1, 2, 3. So the critical path is 3. Okay, for this. Here is 1, 2, 1, 2, 3, 1, 2, 3, 4. So the critical path is 4 right over here. Okay, so the maximum um, uh, length is actually the critical path, which is 4 here. Uh, I should just say 4, but right? I should say 40 here because 4 times 10, so 40. The critical path here will be 30. Okay, so you know that this one should have better performance than the graph on the right hand side. Okay, how about the maximum degree of concurrency? The maximum is actually we already counted 7 divided by 3. This one is also 7, but divided by 4. Okay, so this one has poor uh, what do you call that? Degree of concurrency on average. So when you solve the problem, you should look into this as well because how you decompose your problem or how you tackle the problem will determine how fast your performance can be. Okay, so it appears to us that parallel computing can make we can improve it uh, without uh, any limit. That means we can improve further and further until maybe we get the highest performance, which is close to 0 second. And actually, that is not possible. Okay, we will look into why that is the case later on. Okay, there is some law that this paracomputing is bound uh, and it cannot achieve that performance that we want. Okay, there is certain limitation, and we'll see why we have that limitation later. Okay, and of course, we normally always think like if we want to solve the problem, we can take the call and then solve the problem straight away. You can only do that if, let's say, you are programming at very low level. Okay, let's say for example you are programming in assembly language, then perhaps you can assign the task to each core. But normally, because we don't have access to the core or physical hardware directly using assembly language, because nobody would program in assembly language anyway, because it's very hard to program and also is very lengthy, it's error prone, and it's tedious to program. So we normally use API. So this API is useful because it is developed so that we don't have to worry much about the complexity. That means it water down the complexity so that it's easier for ordinary people to use. Okay, even though you're not specializing in paracomputing, you're able to solve the problem as well. Okay, so we use this API in order to help us simplify our programming. All right. So we cannot, because of that, we cannot assign um, a call to a specific task. So this is done by the API itself. So the API will determine how many cores that it's going to use and how is it going to assign to the cores. Okay. So whenever I discussed just now here, I said that one thread is assigned like this, but underlying allocation done by the hardware might not be the case like what we see here. Okay, so this is what we observe, or this is what we want at the API level, but at the lowest level, it might not be like this. Okay, it will be maybe due to insufficient number of cores at the lower level. Here, maybe I have 4 tasks, but let's say my core is only 2. So at the lower level, here actually appears to be 2 and 2. Okay, so it will be executed at different time because you don't have enough core, right? So that is at logical level, we look at it, we plan it that way. But of course, um, the performance is still dependent on the actual hardware that you have. Okay, so this explain what I mentioned to you. But normally the lower level, that means the API is able to choose the best way to solve your problem. Given what you intend the API to do, they will find the best way, looking at their limited resources, how to allocate it so that it can solve your problem the best it can. All right. So I'm going to skip that. Basically, it just mention what I mentioned to you just now. Okay. Now we have moved on to what we have learned before, which is parallel programming coding style. I will go through very quickly on this part because we have already seen this many, many times in practical. In fact, I've been telling you at every practical, I keep on reminding you this single program, multiple data again and again, right? Okay, and then you have master worker. Uh, like for example, I told you that you got track ID 0, which is the master, and the rest are all the workers. Okay, and it is true for OMP, it is true for NPI, and it's also true for QDAR as well. Okay, so you got master, you got workers. Basically, the master is also a worker. Okay, and then you run in parallel, and mostly when you try to solve the problem using SPMD, which is a single program multiple data. Okay, the place that you look at is always the loop. Okay, the code that is looping, because that is a part where the processing, most of the processing is done. Okay, so you apply the parallelism normally on the loop. Okay, and finally, when you're done, you join, or maybe you put a barrier to wait for one another, and you repeat the whole process again. Okay, the program is single program, but the data is shared, or the data is different for each thread or processes. Okay, it can be shared, it can be also split into individual parts and used by individual threads, which means they are not sharing. Okay, but most of the time, when we solve a big problem, the data is shared. So somehow if you want to process it, it will have to share with the rest of the thread, maybe to continue process it later on, or maybe the other thread is also needing the sharing it. Okay, basically, that is what I talked about just now. You got single program, multiple data, single program run by multiple processor elements. Okay, and each processor element has a unique ID. That is a thread ID that I was talking about all the time. Okay, so you use the thread ID to determine which portion of your data that you need to process. Okay. Um, all right. Even though it's single program, multiple data, but each program element here is actually they're talking about thread, but at lowest level, we don't call thread, we call processor element. That is at the assembly level. Okay. So the QDAR, the lowest level, the core that's running is called processor element or processor engine, PE. Okay, it might follow different path if you have if else statement. So you can choose, like for example, certain range of thread is going to do this part. The other range of thread is going to do the other part of the code. You can actually have if else statement, even though here is a single program, but uh, each thread might be working on different, or each group of threads are going to be working on different part of data. Okay, um, I think I have to sorry, I've moved to another slide because I did not copy that into my Jamboard. Let me get back quickly to that position. Okay, okay, just now we were here. All right, so your master thread, worker thread, you got master thread that is working on the task, and we target the loop. to improve the performance. That is where we apply parallelism. Okay, and once it's done, we uh, we wait for one another before we proceed on to the next stage. Okay, so that is fork join, or you put a barrier there. Okay, normally it's at the end of the process. If it is in the middle process, waiting is bad, so you try your best not to wait if possible. But of course, sometimes you cannot. You have to wait until all reach that uh, point before you move on to the next one. You cannot process until all has already done the job, the previous job. Okay, if you have that kind of case, then you have no choice. Okay, so why SPMD? Mainly because of the hardware, the way we design the hardware. We found out that SPMD is the easiest to create parallel computing, right? Of course, you have met the other three different methods, but SPMD is the easiest when we design on the silicon, okay, the processor on the silicon. And luckily also, most of our problem that we face can be broken down into or maybe massage it so that it become SPMD. Uh, it can be solved using SPMD method. Okay, so even though the problem are different, but you can actually uh, change the program so that it will be able to be solved using SPMD method. Okay. Okay, so the typical SPM program phases, we already seen this many times. I'll just go through very quickly. First, we have to initialize what we need to initialize, whether it's private, whether it's shared. If it is private, then we have to, sorry, if it is shared, then we have to determine whether it is um, it's going to raise. If it is going to raise, then we have no choice. We have to protect it. But try your best not to protect, so try your best not to share, because when you share, you have to use critical region, and critical region is going to harm your performance. Okay. Um, Sometimes it seems like a program has to share, but actually you can do away with sharing. For example, you can create private data and then initialize all of them to the same value. Okay, so even though it is private, but they have the same value, right? So it is not shared. It is private, and therefore there will be no risk condition. And once you compute, you put the data inside there. Of course, you go in the loop, and because of loop, you uh, you spend your time there. But finally, in the end, when you solve the problem, you do only one critical region, one time only to share the data. Okay, so inside the loop, you don't share the data, but you share only when you update the last time. Okay, so sometimes we can overcome sharing by doing that. That means we delay the share until the end, and we only share one time. We don't share the loop multiple times because it's going to be slow. Okay, so that will be the initialization part. And then when we move on to solving the problem, and as we solve the problem, we have to instantiate the thread, and each thread has its own unique ID, and that unique ID is used to determine which portion of the code that, sorry, which portion of the data that is supposed to process. Okay. Then, if let's say you're doing MPI, you distribute the data through the communication media. If you are using OMP or QDAO, basically it share the data only. Okay, you just decompose the memory, and then you pass the pointer to each one of the thread, and the thread will access immediately the memory where the data is situated. Okay, so it's not uh, transmitted through communication media. Okay, you straight away grab from the memory. That's why OMP and QDAO is faster than MPI. Okay, and then you run the core computation, which is a single program, multiple data, and finally finalize the data by maybe converging or reducing the number into one data that you want. Okay, so the core computer phase, you use the ID to loop. Okay, you use the ID as an index, okay, to find the data. Here it says split the loop iteration. And finally, when you uh, uh, achieve the solution, you could just combine them. Okay. All right. So that one actually I have gone through many times in practical. So I went through very quickly here because you should all should know how actually this is done, right? We have done this with own FP, MPI, and some part in CUDA. Okay. Next, we want to talk about the law that I was talking about. Sometimes we think that we can improve the performance by increasing the number of threads. Okay, we can increase like maybe 1 million, maybe. Okay, and we think that, okay, 1 million, that means we get the performance gain should be 1 million times. But that is not true. Okay, and if you look at uh, this law is telling you that a there is a bound, there is a maximum limit that you cannot get past. Okay, maybe I go to, because here there's no diagram, I'll go to internet, Amdahl's law. I haven't shared the image yet. Don't worry, I will share it in a short while because I want to show you this picture. Okay. All right. So this picture actually talks about Amdahl's law. Okay. Before I show you all the equation, it looks scary, but actually it's quite simple. I'll explain how it works. Okay. So Amdahl's law actually describes the upper bound limit. For example, you can see on this x-axis, that is the number of processor or the number of cores that you have. And then the y-axis is the speed up, the effective speed up. Effective speed up means the final speed up that you experience, the final speed up that you achieve. Okay, so we would think that as we increase the number of processor, we think that it's going to go straight line forever, up and up and up in a straight line. But Anders' law tells us that no, this is not true. As you increase the number of cores, somehow it will saturate. For example, this green line here, okay, is saturate at 20. That means the performance gain, speed up, effective performance gain, which is the speed up in this terminology used by Anders, is speed up. Okay, I always use performance gain, right? And I purposely choose a performance gain because I don't want to mix up with this speed up. Okay, the speed up actually has a different meaning, right? So the speed up is how fast compared to single thread, similar like performance gain that I was talking about. And later I will explain what is the difference between the term that I use and the term that you use here. Okay, so this here is also speed up, is comparing the effective performance compared to single thread, okay, without any parallel computing. So here is 20 times as fast as the serial code. Okay, as you can see, it does not go up and up, but it will saturate at one point. It's saturate at 20. Okay, and that one is if you can parallelize 95% of the code. Okay, and why this percentage here, I'll explain to you later. Okay, if let's say you can only parallelize 90% of the code, okay, your performance gain, or your, I should say, speed up rather than performance gain, the speed up is 10 only. All right, even though you increase here, you can see that I can increase to 1 million here, but here will not improve much. Okay, it will be more or less about 10. All right, if you can parallelize about 75% of your code, then you'll get only 4 speed up. Okay, and if you can um, parallelize 50% of it, you get only 2. Yeah. Okay, even though you increase as many as you like, you will not see any performance gain from there. So our intuition tells us that as we increase the number of processor, we should get a forever increasing performance gain. But this Amdahl law tells us otherwise. It says no, actually it's not true. And why is that so? That is a part that I'm going to talk about now. Okay, let's get back to our um, okay. Now I get back to here. Okay, there's some terms and notation. There are a lot of formula here. There is a meaning to this formula. I will only use, actually, we have to know all of this, and you'll see all of this as well. Uh, but I want to focus on this one first, because if I introduce to all of you all this, is going to be quite scary here. If I know that there's only a few equation here, but as a beginner, you do not know anything. You're like, oh, this is very scary. Okay, but I want to talk about only two equation at the moment. Okay, these two equation. The first one is the S. The second one is a parallel fraction, which is P equals to 1 minus S. Okay, what is S? S is the amount of code or the amount of time spent on serial part of your code. Okay, if you run your code, right? Uh, if the code cannot be converted into serial, cannot be converted into parallel computing, okay, that part is called the serial part. Okay, the serial part of the code which you cannot convert. Okay, for example, I mentioned to you there are certain cases, like for example, Fibonacci sequence. Okay, if you want to compute them, it can be quite problematic because it dependent on other part of the data, right? So your code, even though you want to parallelize them, you cannot parallelize this type of problem because the nature of the algorithm is it depends on the previous data. So most of the code is actually depend on other piece of data coming from other thread. That means they have to wait for one another, and therefore you cannot run them in parallel. Okay, so here if we cannot achieve um, uh, parallel computing, that part of code will be called as the fraction of code or the fraction of time spent to in your computation that cannot be run in parallel. Okay, so that is S. And how about P? P is a part of code where you can parallelize. Okay, there's certain part of code you can parallelize, certain part of code you cannot. Right. So the one that you can parallelize, okay, that fraction we call P. Okay, the fraction means in terms of percentage or in ratio. Okay, so the part that you cannot parallelize is called S. Okay, so if it is in fraction, that means it must be from 0 to 1, right? How about P? P also the same thing, is the section of code where you can parallelize. Okay, so the one that you can parallelize is called P fraction, and the value also from 0 to 1. Okay, so if you combine S plus P, that is actually 1, all right? Because this S here is the part of code that you cannot parallelize. P is a part of code that you can parallelize. So you combine these two, S plus P, it must be equals to 1, isn't it? Right? Okay, so let me sketch it here. So, okay, so what I mean here is S plus P must equals to 1, right? Because S is fraction, P is also fraction. You combine all this is basically your whole code. This is your whole code. X plus P is 1. That means 100%. That means that is the whole code. Some section you can parallelize, some section you cannot, right? And if um, you do some algebra on this equation, you just move your s to the other side, you get 1 minus s, right? So this is the one that you see here, okay? Okay, so only these two that I want to talk about. The rest actually will come naturally as I explain. So I'm going to move on to the next slide. Okay, what this Amdahl's law is saying is this. When I say S and P, right? So normally when I told you in a class, I always assume that the whole code is able to be parallelized. Okay, so I'm assuming 100% code is able to parallelize your uh, your S is going to be 0, your P is going to be 1. So I assume that. Okay, so when I say performance gain, I always assume that the whole code, 100% of your code, can be parallelized. But actually, it's not true because there are certain part you cannot parallelize. And that is what this Amdahl's law is talking about. And because of this S, which is not 0, okay, it has certain value. That is the reason why we see this graph here. This graph, you see, it goes and then it saturates at this point here. The reason why is because of the S. Okay, we will see later clearer why this S, when the number is not 0, you have a limit. The limit here for this is 20, right? So the green line, it says here, the green line is 95%. 95% here, that means the P is 0.95. Your S is 0.05. Okay, so your performance or your speed up saturate at 20. All right, and for this purple line, that is 90% can be parallelized, 10% cannot be parallelized. That means 0.9% and 0.9 of your code can be parallelized. 0.1 of your code cannot be parallelized. Okay, if you run them, your speed up maximum you can achieve is only 10. Okay, so that is the difference between the terminology that I used before, which I always say is performance gain, right? I assume that the P is 1, the S is 0. But here, actually, the actual problem is not always like what I always imagine. It's always um, S is never 0. It's always a number, right? So the 50% here means that 50% of your code can be parallelized, 50% cannot. So your performance speed up that you could achieve is only 2. And that is the reason why that you see uh, sometimes we use 16 thread, right? So the best performance that we should expect is 16 times, but we don't get that. We get only 2.5 times, 4 times, 5 times maybe. That is the reason, okay? Because of this Amdahl's law. That's why you see that the performance does not exceed a certain number. Okay, for example, in this case, say it 2, even though I got 65,000 threads that is running or processor, but then the performance for 50% uh, 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 code that has been parallelized, but 50% cannot be parallelized, the performance gain is only 2. Okay, so this this graph that you see here actually comes from this equation, which I'm going to show next. Okay, it comes from this equation. So let's look at this equation. I know that you can memorize this equation, but actually, if you think carefully, you don't have to memorize it because it's quite logical. This equation is quite logical, especially the one on the left-hand side. We start from the left-hand side. Actually, these equations are all the same. The left-hand side is the same as the middle. It's also the same on the right-hand side. Yeah, I'll show to you why. But let's look at this one because I don't memorize this equation. I just remember how actually it's computed. That's all. Okay. How do I uh, uh, memorize it? Okay, this is the speed up. Okay, the speed up. Unfortunately, it is also denoted by S, but this is capital S. There are two S here. Okay, in this slide, in this slide, we use capital S to indicate speed up. The small letter s is a fraction of code that cannot be parallelized. Okay, it has to be run in serial. Okay, small letter p is the one that we can parallelize. So capital S is the speed up. So don't get mixed up. Okay, so the speed up is the one that I always talk about, the performance gain, the performance gain. So whenever I compute the performance gain, you always see that I compute this way. I'll write it down next to it. Okay, I always do like this performance. Oh, sorry. me delete this because I accidentally pressed the button. So performance, let's see. Okay. I always, what's happening? Maybe I pressed the button. Yeah. The eye refused to appear. Okay, never mind. Okay. So the performance gain is I always do uh, uh the the part that I can parallelize. That means is P. Okay, and then P plus S. Uh, oh, sorry. So there's no P there. There's S on S. Okay. So my performance gain, I always use this, right? This formula, P divided by S. Okay. Because I assume all my code can be parallelized and I compare with the serial performance. So this is going to be my performance gain. Okay, let's look at this Amdahl's law. But the Amdahl's law, remember I mentioned to you, certain part of code can be parallelized. The other part of code, it cannot be parallelized. Okay, so what is at the top here? At the top here, I assume that uh, this is the enhanced one. Okay, this one is the original, right? The top one enhance. Enhance means I use parallel computing, and I get this performance P. Okay, uh, is the enhanced one. This is the original. That means the performance that I get running using serial alone. All right. So the top one is enhanced. The bottom one is original. Now let's look at this code. This formula here. At the top here is also the enhanced one. The bottom one is the one that is the um, original. Okay. Now if you look at the top here, okay, and if I say uh, my S is 0, okay, if my S is 0, that means I can parallelize all the code, right? So my S is going to be 0. So I have the P only at the top here, right? Okay, all right. And then here is also 0, okay? And this one P is because I can run in parallel. I assume that I can run in parallel, all right? And this P is going to be the performance gain, okay? The performance gain after I run n number of threads, okay? N here actually is the n number of threads, okay? So if I take that performance P divided by n, isn't that the same as S? It's the same as S, isn't it? Okay, so that's why here, this formula, if you assume like what I assumed just now, S is 0, P is 1, okay? So here I get P, here I get 0, here is actually I get Sn divided by n. So Sn divided by n is actually uh, S. That's why I get back here. Okay. So that means Amdahl's law actually is more general than my formula. Okay, my formula here actually derived from this Amdahl's law. Okay. Um, okay, the one that I was talking about, the efficiency here, E, S, uh, S divided by N. I shouldn't show to you that maybe because I'm afraid that you get confused. Just now I make this assumption, right? I'm not sure whether you understood what I explained or not. Okay. So here I'm assuming that if let's say my P is 1, my P, not sure my pen is something wrong with my pen. Keep on deleting. Okay. Okay. So if my P is 1, okay, and that means if I use N thread. Okay, isn't it S, sorry, P equals to S multiplied by N? It is, right? Okay, so the performance gain that I get is actually uh, uh, this Sn. Okay, then if let's say I plug this into here, oh sorry, if I plug this equation into here, okay, then I get this. I plug this into here, I get this result here. Okay, now this is not interesting because this is not always true, but I'm just trying to explain to you why I use this earlier on. I use this because I always assume p equals to 1, and I'm lazy to go and check which one actually cannot be parallelized and then take into consideration. But in actual fact, we have to take into the account this s. We cannot assume that p is always 1. Okay, that is what I'm trying to say. Okay, so the equation is this: s, the speed up, is actually the total, okay, the performance, that is s plus p divided by this s plus p divided by this n. Okay, the parallel part is the one that you can improve. So if you divide by n, that is the performance gain that you get here. All right. Okay, so when you rearrange it, for example, in this case here, we know that s is equals to, okay, s s plus p is equals to 1, right? So if I substitute this into here, I get this 1. Am I right? Okay. That's why these two equation is the same. Okay. The left hand side equation and the middle equation is the same because s plus p is 1. This is a 0. This is a parallel. Okay. This is the whole code. The whole code is 1. All right. So here is 1. Okay. Now how do I get from the middle to the last one? It's basically just divide by n. So if I multiply here by n, and I have to multiply the denominator by n as well, right? So it's like n divided by n. That's why I get here 1 times n is n, s times n is sn, p divided by n times n is p. So basically, all these three equation is the same, okay? But most of the time, we will be looking at this middle equation here, okay? In the exam, now I'm talking about exam because, as I told you before, this one will come out in exam. We always look at this equation here. Okay, but how do you derive this equation? Actually, derive from here, or maybe you can derive straight away from here. Okay, so this is the whole program performance. Okay, p s plus p, which is basically uh, the performance for both part of the code. Okay, and then divided by s plus p divided by n. Why we divide here? Because there will be performance gain here. Okay, so if you divide, then this denominator will be smaller, and therefore this s will go up. Okay, will go up. That means they'll have higher performance. That means your n increase, your s will increase. Okay, because your p divided by n is going to decrease, right? So you will see the speed up will increase, but if you increase to infinity, you get this one to become 0, right? So you got 1 over s. Actually, 1 over s is the one that you see here. Okay, the one that you see 20 here is because 1 over s. Okay, that 1 over s for the green one is 5%. Okay, 5%. That means 0.05. You will take 1 divided by 0.05, isn't it 20? It's 20, isn't it? Okay. How about the purple one? The purple one is 90%. That means your S is 10% or 0.1. Okay. Remember I mentioned to you if n increase to infinity, your P divided by n is going to be 0. So your equation S is going to be equals to 1 over S. Okay, 1 over S, 1 over 0.1. Isn't that 10? That's why here is 10, right? So actually, like what I mentioned to you, that equation actually tells you how the graph look like. So the graph look like this. Okay, for the equation that I explained to you just now. All right. Okay, so let me write it down here much clearer. Okay, if uh, your your n increase to infinity, okay, that means your s is going to be 1 over s plus 0, right? So this is equals to 1 over s. Take note, and this one is capital S, this one is small letter s. I should draw it bigger, okay? So there's a speed up. This s is the portion of code that cannot be parallelized. Okay, at the bottom here, it talks about another law which is a Gustafson law. So I'm going to skip this last two uh, statement here to later part, okay? Because if I explain it now, it will be a bit confusing there. Okay, so what kind of question that will come up? Oh, sorry, I forgot to share the screen. Just now I just draw this equation. Okay, if n goes near to infinity, your capital S speed up is going to be 1 over S plus P over N. P over N is going to be close to 0 because the N increased to infinity. So that's why it's 0. Okay, P over N increased to infinity, P over N is going to be 0. Okay, so overall it's going to be 1 over S. So now this small letter s is the portion of code that cannot be parallelized. This capital S is the speed up. Don't get confused. Okay, so let's come to look at the problem. Okay, you have to focus on this because, as I said before, the exam there is one small part of it will be on this part here, which is Amdahl's law. Okay, you just need to remember the formula. This formula in the middle. This one. Okay, this one will not be given. You have to memorize this. If you know how to explain yourself, you can actually derive this, but you can also memorize it. I think memorize is safer so that you can understand it also, and then you can remember it as well. Okay, so the speed up is in words, actually is this. In formula is actually this. Okay, so this one is in words. Okay, in formula it looks like this. Okay, so let's have a look at the terminology that we use here. Right. Uh, Let me check. Is it? Yeah, it's correct. Okay, so now I have to do some changes here. If you look at this equation, is 1 divided by S plus P divided by N. Right? I'm going to write it down here. Okay, I'm going to write over here. Uh, S, the capital S, equals to 1 over small letter s plus P. Uh, any problem? You can't see. Can you see now? Because I can see on my screen. Can you see? Oh, yes. Okay, good. You can see, right? Okay. So 1 over, I actually copy this middle part here to here. Copy to here. Okay. Uh, Now this formula that you see at the bottom here, okay, I want to derive to here. I want to derive to this. Okay. So this is actually equals to 1. Now S, remember the S plus plus p, isn't it equals to 1? Is it equals to 1, isn't it? Okay, so I'm going to replace that here. So here, this one is equivalent to saying s equals to 1 minus p, isn't it? Okay, so I'm going to replace this s with 1 minus p. Okay, and put in the bracket plus uh, the fraction is the same, p divided by n. Okay, why do I do that? Or why this formula is doing that? Because if we look at the original one, you have small letter s, p, and n. So there's three variable there, right? But actually, this s plus p is equals to 1. So this s can be replaced with 1 minus p. But if you look at the new equation, there's only two variable, p and n, instead of 3. That's why we prefer this last equation. And this last equation is this this one that you see on the left hand side. Okay, this equation is actually this one. All right. Okay. So that p is called fraction enhanced p, fraction enhanced, meaning that why is it called fraction enhanced? Because that is a code that you able to run in using parallel computing. So that is a fraction that you can enhance. That's why it's called fraction enhanced. So p is fraction enhanced. Okay, and then the n is the factor of improvement. Why is that so? You can imagine n is the number of your core or the number of processor. All right. So that is a factor of improvement. If I say n is 3, that means I can I can enhance or I can have a factor of improvement of 3. That means 3 times faster. Okay. But I may not achieve that because if my P is 1, yes, I can achieve N. That means my performance gain is N. But as I said before, because the serial part, there are some code which is not able to be changed to parallel computing. It remains as serial portion of code that cannot be parallelized, right? So because of that, our speed up here will never equals to N, okay? If let's say my s is equal to 0, perhaps I can achieve this n here, but unfortunately I cannot. Okay, I cannot attain that for that reason. Why do I do it? Why do I say that? Because if you look at this equation here, let me write it down. This s here, this s here. If let's say my s plus p is 1, I'm sure where my pen is. Like that, kind of strange. Okay, let's say my s is 0, so my p is going to be 1, isn't it? Sure. So if let's say s is 0 plus p, I'm sure why my pen not able to write properly. Hmm. Sorry, let me find out why my pen 0 plus p equals to 1. P is equals to 1. Is that correct? So if you see that, then you get 1 over 1 minus 1 plus 1 1 divided by n, right? Okay, so this one is 1 over 0, 1 over n. Isn't it is n? Okay, so if your performance, if you can parallelize all your code, that means your speed up and your n is the same. You know? So that's what I'm talking about here. So that means you every time you increase your number of processor, your speed up also increase linearly. Okay, but this is impossible because of the s, which is not 0. Okay, so you can see here, this is what I always assume. If p is equals to 1, your speed up and your factor of improvement is the same. Okay, if you got 100 cores, that means your factor of improvement is 100. Your speed up will be 100 if your p is 1. You understand? Okay, so I hope that you understand how what is the meaning of this and why do they call with this name. Okay, now let's look at the example. Let's take the speed up be denoted by s. Okay, the fraction enhancement, we write it as fe rather than p. So we're not going to write p, we're going to write it as fe. Okay, so fe is p. Fe is actually p. Hmm. Okay, and my fi is going to be my n. Okay, so let's use that term. So we got factor of improvement is n, factor of enhancement is p. Okay, so this is the terminology that we use here. And I think in exam also I use this terminology because I don't want to confuse you all. So I use the same terminology here as well. So remember, FE is factor of enhancement, which is the part of code that where you can parallelize. FI is how many core that you use, okay, in order to solve the problem. Okay, so there are three different problem types, which is this one. The first one, it's to determine S given Fe and Fi, determine Fi given S and Fe, determine Fe given S and Fi. So there are only three possible kind of question only. Okay, either the first one, second one, third one. Okay, given the other two, you try to find the other variable because you got three unknowns here, right? So let's say, for example, in this first exercise that we will see next, given factor of enhancement and factor of improvement, that means P and N, try to find the S. If you remember this equation here, this equation here, all right, then you should be able to solve this problem. Okay, for this next one, is actually this equation as well. This n is fi. You just bring it up to left hand side and then s to the right hand side. Then that we have a new equation, right? So that one will be that other equation is for the second one. The third one, you have to bring this p to the left hand side, s to the right hand side. So you have to start from here and then find the appropriate equation to solve this. Okay, and there's something that you have to take care. I'll show to you later. The first one maybe you don't have to worry, but the second and the third, I think you have to take care a little bit because of the n. Okay, you have to find whether your answer is actually valid or not valid. Okay, let's have a look at the first one. So given Fe and Fi, Fe is the P, Fi is the N. All right. So it says if we know Fe, Fi, we want to compute the speed up S. Let's assume that the program have 40% of its code enhanced. Enhanced that means it can run in parallel, 40% only. That means 0.6% cannot be enhanced, cannot be made to run in parallel. Okay, it has to run in serial. Okay, to run 2.3 times faster, so your Fi is 2.3. 2.3 here is because there is a factor of improvement. Okay, and of course here it's kind of funny that we can put 2.3 because normally I tell you that the number of processor, right, is integer, but in Amdahl's law we can actually have a factor of improvement which is in fractional like this, 2.3. Okay, we don't care, we just use it, right? So this is our n, or your factor of improvement. Okay, it run 2.3 times faster uh, for the code that is running in parallel. All right, and if you remember the formula was this, right? This is P, this P over N, right? So basically, this is the equation that you see here, this equation here. Okay, so you just plug in the value. Okay, 1 minus 0.4 is 0.6, which is your S. Okay, plus P over N, which is a Fe over Fi. Fe is 0.4, Fi is 2.3. So if you divide the two, you get 0.174. Okay, and you add this and you take 1 over that value, you get 1.292. Okay, so is the speed up. Okay, so imagine this is the N. That means this is the maximum achievable. You cannot exceed this number. So in order to check, this number cannot exceed this. If it exceed, that means your computation is wrong because the N is the maximum. Your speed up can never achieve that. Okay, it can be the same if your P, that means your factor of improvement is 1. Okay, if your factor of improvement is 1, this value and this value can be the same value. Okay, but it cannot exceed this value. So you better check that when you answer your question. Okay, now I have to move on to the next one. Okay, you all can see this screen, right? Okay, I'm moving on to the next slide. Okay, problem type 2. Type 2 problem is um, determining Fi, that means factor of improvement, given as speed up, and Fe, factor of uh, enhancement, which is the P. Okay, so how's the question might look like? It look like this. Let a program have 40% of code enhancement, the same thing as just now. Fe is 0.4. Okay, and the speed up is given as 4.3 times faster. Okay, and take note that the term that we use almost the same, times faster, because speed up is the effective enhancement. Okay, or improvement, I should say. Okay, this is the effective factor of improvement. The Fi is the uh, I should say the maximum factor of improvement. This is the effective one. Okay, so that's why the term that we use is time faster. Just like the factor of improvement, we also use 2.3 times faster, right? So we use the term time faster. Don't get confused. The unit is the same, is time. Okay, but then the meaning is different. S is the effective factor of improvement. Fi is factor of improvement, the maximum factor of improvement. Okay, so given the effective or the speed up, 4.3, and it asks you to compute the factor of improvement, Fi. So what you need to do is you start from the original equation, you just move around your variable, use your algebra, okay, and you get to this, uh, sorry, actually it shouldn't be this. It should be, okay, it's not given there. Okay, uh, but what you can do is you can find the equation first, then you plug in the value, or you plug in the value and then you find the equation. Okay, before you find the equation, remember I mentioned to you, you have to check first whether your answer is going to be valid or not. So how do you check the answer is valid? First, you don't uh, you use the original what I call it equation. Okay, and then what you assume is this: your Fi goes to infinity. Okay, if your Fi goes to infinity, then you will see that you get to this equation. Okay, okay, you get to this equation. Why this equation is there? Because 1 minus Fe, this one Fe divided by Fi. Fi go to infinity, this term here becomes 0. So what is left is 1 minus Fe. That's why you get 1 minus Fe. So the Fe is actually P, right? So 1 divided by 1 minus P, okay? P is 0.4. Okay, eventually you get to this answer here. Okay, you have to take note. This is not the answer yet. This you have to take note. This is to indicate that that is the maximum speed up that you can achieve. Okay, this is the maximum speed up that you can achieve. But it asks you to find from what is given here, find where s equals to 4.3. So we know that from here is not achievable because remember I mentioned to you that s has a limit. We are asked the question asks you to try to find this 4.3. You cannot. No matter what kind of n that you want to find, you cannot get this 4.3 because the maximum speed up, the effective speed up is 1.6. And that can happen only if Fi is infinity. That means you have as many cores running the parallel computing part, and this is the best that you can achieve. Remember this diagram that I was talking about? This diagram? You see this maximum here? No matter how many cores that you apply there, your factor or your speed up cannot go beyond 2. Okay, the questioner asks for 4.3, which is above what you can achieve. So you cannot, right? So your answer should be this is not solvable. Okay, there's no solution to this. Okay, because the maximum is 1.67. Okay, so this is not achievable. So for type 2 kind of question is a bit more tricky. Okay, there is no solution here. Okay, so you have to find whether there is a solution first using this formula. Okay, let's look at the third one. The third one, given S, given Fi, you have to find Fe. Okay. Here also the same thing. You have to find the maximum possible speed up as well. Oh, sorry. Okay. Sorry, I forget to change to this. Okay. The type three, the third question is also the same thing. You have to um, find the maximum speed up. Okay. Just the same as this. You have to, yeah. What's the question? Mm, Any question? Okay, you all can see, right? Okay, just now, let me repeat again because I think I did not show you this picture just now. Okay, what I'm trying to say here is this S here, you need to find out first, assuming that this Fi goes to infinity. That means you have a factor of improvement of infinity. That means infinite amount of core that you apply on the parallel computing code, which is the Fe, and your effective speed up can go up to 1.67 only, right? You cannot go beyond that. But the question asks you for 4.3, which is beyond this. So you know that this is not achievable. Okay, your answer is it's impossible to achieve. That maximum S is 1.67. You cannot achieve 4.3. Okay, so if the question asks you for this, you know that you cannot achieve, and your answer should be there's no way for you to get that, right? Because of the Amdahl's law. Okay, the third question also the same thing. Third type of question where given S, given Fi, asks you to find Fe. Fe is the factor of enhancement. Given speed up, given factor of improvement, which is the N, right? And you have to do the same thing. You have to find out the maximum possible speed up. Okay, so if you apply infinity to this Fi, you find out your S is going to be 1.3 only. Okay, all right, it cannot go beyond that 1.3. All right, so that is how you compute that and then look at what is it asked for. So if you ask for, let's say 6, then you know that it cannot achieve. Okay, so your answer should be it cannot be achieved. All right, so this question says if P is 40%, that means your Fe, factor of enhancement, is 40%. It asks you whether it's possible to go your S, your speed up can go up to 1.3 times faster. So we found out that yes, we can, provided that your Fi goes to infinity. Okay, so that is how you check it. Okay, so this question is asking whether it's possible to get to this speed up or not. So our answer is yes. If you go, if you set your Fi to infinity, you can get it. All right. Okay, the last one, um, the last one is if you know Fi as, okay, we find the Fe, and this one is also the same thing, right? Yeah, it's the same as what we have seen just now. Okay, so here is uh, here we don't have to worry about the in, infinite fi because we are looking at fe. Okay, so you just apply the formula, the original formula, okay, and then you rearrange it. You should be able to find your fe. Your fe is in this case is 0.929. Okay, I will not go through this because it's quite straightforward. You just apply the number inside there. Okay, three unknown variable. Two is always given. One is asked from you to calculate. Okay, the one that is tricky is when you find the speed up. Okay, for example, it tells you, I want you to find the solution with a speed up of 6, for example. First, you have to check whether that speed up is achievable or not. If it is not achievable, then your answer should be no. Okay. Now, how about the rest? The rest actually is not a problem. You don't have to do any checking there, only for the speed up that you need to check. Okay. So that is the thing that I need to tell you for the exam, because the exam, one of these three type of question will come up. Okay. But it's quite straightforward, as I mentioned to you many times. You just need to remember the uh, equation and then apply the formula. Okay, and you also have to remember this formula that I was talking about. This equation, sorry, s plus p is equals to 1. Okay, why is that so? The zero part plus the parallel part of your code is 100%. 1 means 100%. Okay, that means the whole code. Okay, this equation and this equation that you have to memorize. Then the rest is basically given. You just uh, plug it in. Okay. Okay. The last part is actually Gustafsson law. Actually, there's another law uh, because actually Gustafsson has quite a good observation. He said, yeah, Amdahl's law is true, but then we can improve more better than what Amdahl's law is talking about. Okay, so he gave his viewpoint. He said, um, Amdahl's law, when he formulate the formula, he is only looking at the same problem size. Your problem does not change. Your problem is fixed. If your problem is fixed, then what Amdahl's law say is true. Okay, but then he said, the problem that we solve, actually we can scale that problem. Okay, so we don't solve small problem, we solve bigger problem. If you have more processor, we don't solve the small problem. We solve even bigger problem. That means we scale to a bigger, larger size. Because we have more processor, that means we are not. If we want to achieve performance gain, we should also scale the size of the problem. So that is what Gustafsson is saying. Right? So he said if you want to increase beyond Amdahl's law, you have to increase the problem size. Okay. Somehow, Gustafsson law also will, if let's say you don't increase let's say you scale the first time, but after that you don't scale anymore. You keep on increasing the number of processor and your problem size is you scale only one time. Let's say you scale 5 times bigger than the original, and then you keep on increasing your n. Eventually, the Amdahl's law will uh, become dominant. Okay, so in Gustafsson law, it says this: if you can increase your processor, you better increase your problem size as well, because if you increase both of them, you can see your performance keep on increasing. That is what he's trying to say. But eventually, if one stay stagnant, doesn't change, the other one keep on increasing. For example, the size keep the same, and you increase the processor, you are still bound to Amdahl's law. So if you want to overcome that Amdahl's law, you have to increase also the problem size, not only the processor size. You also have to increase uh, the the problem size as well. So your n increase, your problem size also should increase as well. So if you increase these two, that means now uh, you have a performance gain that is bigger. Good night. Okay, so that is what Gustav Holm is talking about. All right, and this is the point also that I talk about when I ask you to do your assignment. Remember, I told you that your problem size cannot be small. Why? Because I'm looking at this Gustav Holm law. This Gustav Holm says if your processor is big, now big means you have many cores, you should increase your size of the problem. Because if you don't increase the size of the problem, then you're bound to this Amdahl's law, and therefore you don't get any performance gain. Now, now I hope that you understand why I always tell you, your problem size, don't keep it too small. Don't take it like 10 kilobytes. Some of you tell me, oh, I want it small. I know why you come to me and asking for small size, because simpler, right? But if I tell you yes, go ahead, you won't see any performance gain because of this Gustafsson law. Okay, that's why I keep on telling you, use large number. Large number is because of this. All right. So unfortunately, uh, there's no exercise for this. Okay. The formula that we use is still the same like Amdahl's law, just that we increase the size of this the problem size of this SMP. That's all. Okay. That's why you see the n here is there. Okay, because of Gustafsson law. Because when you increase the n, your problem size increase, right? So somehow your formula will be slightly different. Okay, so this is the equation, but I will not go through it. I'm just telling you uh, the Gustafsson law exists, and it states there what Amdahl's law say is true if you fix your problem size. You don't increase the problem size, but you increase only your processor. But you can improve your performance if you increase both of them. You increase the problem size, you also increase your number of processor. And this is what Google is doing. Okay, you know why Google can become number one in search engine? Because the problem is very big, and that's why they can scale. They can scale the problem. They can scale their number of processor. That's why they get a lot of performance gain, okay, or speed up, in the terms used by Gustafsson and Amdahl's law. All right. Okay, I hope you understand why I always tell you to increase the size, because if you increase the size, you have less chance of facing a problem like what I mentioned to you, where you see the performance cannot be increased anymore. It's stagnant after a while. Okay, so that is for that part. Now the rest of the part, I think I will not discuss anymore because we already discussed this before. Uh, how we uh, partition our problem when we solve the problem. Okay, let's say for example, we have programming massively per processor. We want to find um, the histogram of these letters appearing. How many times that this letter appear? How many times P appear in this word? How many times R appear in this word? All right. So we can actually solve using serial, where the program will look at each one of them and then put it into this bin. Okay, this bin is 0 to D, E to F. Okay, when you see P, P should be inside here. R should be uh, in between here, right? Oh, sorry, here. Okay, so O should be around here, all right? So if you put it into this bin, then you create a histogram, right? But if you use serial, it's going to be slow. That's why you run in parallel. Okay, let's say you got four parallel tasks. One task is to do programming. The other task is to look at the massively. And the third one, parallel. The last one is processor. Then they can run in parallel and put it into this bin. And by right, it should be running faster, right? But if you partition it this way, everybody is sharing this bin here. They're going to race with one another. So you have to use a critical section. So when you enter this critical section, it's going to be slow. Okay. So we don't advise you to do this. That's one thing. Second thing is, in terms of memory, you can see that this memory is going to be quite large, because they are looking at different part of the memory. So it has to go into the cache, and you do not have enough cache. Okay, your cache size is small, so this is not ideal. Okay, the better way is actually uh, to do it this way. Okay, so instead of doing block decomposition, you do cyclic decomposition. The reason is because 1, 2, 3, 4, all this is done by 4 tasks, and it occupies small memory. Okay, and then when this is finished, you move on to the next data 1, 2, 3, 4. They are adjacent to one another. But if you look at the previous one, we do block decomposition. This thread is looking at this block. The other thread is looking at the other block. That means all these blocks need to be inside the cache at the same time when they solve this, right? But this cache cannot store all of them. Your cache might be small. So it's going to be trashing. You have to load it, used by thread one, and then you have to load another part of the data into the cache, which is used by thread number two, for example. So they're going to trash one another. That means the memory is keep on copying into the cache and then delete and then copy again into the cache and then delete because of the thread is using different part of the memory in the RAM. Okay, but then if you coalesce them like this, coalesce means you group them together like this. That means 1, 2, 3 is focusing on this part of data, and it can fit inside your cache. Okay, once you're done already. So you move on to the next one, 1, 2, 3, 4. All right. So this is the part of the data that you put into the cache in the next iteration. All right. The third iteration will be this, the fourth iteration is this, the fifth iteration is this. That means in each iteration, your size of memory inside the cache is always very small, and you read only what you need to run your code in parallel. Okay, so this I already discussed with you before. Why we want to effectively use our memory, and we have to partition our data or decompose our data in cyclic manner, which is much better than block manner. Okay, but if this one is true only for MPI, sorry, for OMP and QDAR, okay, because QDAR and MPI use local memory. If you are talking about MPI, it's different. MPI because you're working on different computer, right? So on different computer, you don't want to be cyclic. Cyclic is going to penalize the performance. So MPI will do very poorly if it is cyclic. How do we solve that? We solve it by using block, because each computer will have its own data, right? So imagine this is one PC, this is another PC, this is another PC, and this is another PC. So each PC will have one process to run, and they run in parallel, right? And because they're independent, they can run at the same time. So for MPI, it's better to use block decomposition. If you are using OMP and CUDA, it's best to use this cyclic decomposition. Yeah. So that is all that I have for today, because the others is actually talking about the same thing. You can see here 1, 2, 3. So 4 different tasks working on at the same time on the data which is adjacent to one another. Okay. So with this, I finish this lecture. Next week there will be only presentation. Okay. So I'm going to use uh, Tuesday lecture as presentation as well. Okay, so the presentation, I hope it can be in CC203. I try to book on Tuesday. So those who did not manage to complete your presentation, please do so as early as possible. I don't want to delay until end of the day of next week, because I want to release your mark as soon as possible. That's one thing. Okay, second thing is there will be a test, final test. And this test is going to be contributing 50%. The other test, the midterm test, will contribute another 50% of overall tests. Okay. And this test will contribute, I think, about 40% of your total coursework. Okay. Why do I do that? Two reasons. The first reason is because this test is going to have some hint about your exam. So please study first before you go for your test. Okay. And I will provide answer for this second test as well. Please read it before you go in for your exam, because it has some hint about your exam. the first test, which is the midterm test, also have hint about your exam as well. So study these two tests before you go for your exam. Okay, so that's the first thing, right? The second thing is about your presentation. Please come with knowledge about your presentation, because this morning when I asked, some of you have no idea what you're doing, okay, and some of you also did not do very well. So I asked the student to redo. I give the student a chance. Okay, so please make sure that you come with an idea of your topic, not just go there and then present without knowing. Because when I ask question, I'll know already whether you understand or you don't understand. Okay, so I hope that next week, those who present, please make sure that you come with knowledge about your presentation. Okay, that's all for today. I end here. I'll see you next week. Okay, if you have a question, you can ask in Google Chat. Okay, thanks. Okay, this is recorded. You can view it if you came late just now. You can